Today, I would like to introduce our team's course project, development of a simplified customized knee prosthesis prototype using low-cost advanced manufacturing tools. First, let me introduce our team members. From left to right, Ji Ming Hao ID, TA25052, Ding Hao ID, TA25051, Fang Zuan ID, TA25053, and Wang Jie ID, TA25040. This project was designed for the course Advanced Manufacturing Processes BTT 3443, with the core objective of applying advanced manufacturing concepts in a resource-constrained educational laboratory environment using low-cost tools. Before initiating the project, we observed that commercial knee prostheses rely on high-end manufacturing technologies and complex biocompatible materials, which are rarely accessible to students. Therefore, we established 4 key goals: designing a modular and customizable prosthesis prototype suitable for student fabrication, completing the production using laboratory-accessible FDM 3D printers and 2D laser cutters, verifying the dimensional accuracy and surface quality of the prototype, and establishing a replicable prototyping methodology. These goals not only align with the course requirements but also help us translate theoretical knowledge into practical skills. The prototype adopts a modular design consisting of 3 core components: a 3D printed femoral component where complex anatomical curvatures are simplified to avoid printing failures, a 3D printed cylindrical tibial stem with a uniform diameter for easy customization and modification, and a laser-cut transparent acrylic baseplate that provides structural support while enabling intuitive observation of assembly alignment. For materials, we selected laboratory-accessible PLA filament and 3mm transparent acrylic sheets, with the total material cost controlled at 260 MYR, fully meeting the low-cost requirement. The manufacturing process strictly follows industrial-grade rapid prototyping standards. First, digital modeling is performed using Tinkercad to support real-time dimension modifications. Then, 3D printing is completed with the Creality Ender 3v2 printer using optimized parameters: nozzle temperature 200 degrees Celsius, bed temperature 60 degrees Celsius, print speed 50 mm per second, and the base plate is processed with the Trotec Speedy 100 laser cutter power, 60%, speed 30 mm per second. Subsequent post-processing is conducted using 400/800 grit sandpaper, followed by manual assembly. Quality verification involves measuring key dimensions with a digital caliper of plus or minus 0.01 mm precision and evaluating surface quality using an optical microscope. After 6 weeks of dedicated efforts, the project achieved excellent results. The average dimensional deviation of the prototype was only plus or minus 0.12 mm, lower than the target limit of plus or minus 0.15 mm. Post-processing with sandpaper completely eliminated layer lines and loose filaments on the 3D printed parts, significantly improving surface smoothness. The entire prototype was assembled within a budget of 300 MYR, and practical issues such as printing warpage, laser cutting residues, and measurement errors were successfully resolved. More importantly, the digital design gives rapid prototyping, gives post-processing, gives quality inspection workflow we established is not only applicable to this project but also transferable to other engineering scenarios such as automotive components and educational models. During the project implementation and results summary, we also sorted out several key questions and their answers. The first question is, why was PLA chosen instead of medical-grade materials? The answer is clear. PLA has a low printing temperature, minimal warping, and simple post-processing, making it highly suitable for student-operated equipment. In contrast, medical-grade materials are costly, require specialized equipment, and since the core of this project is to verify manufacturing principles rather than clinical applications, biocompatibility is not a necessary consideration. The second question is, what equipment was used for the project, and what were the selection criteria? We used the Creality Ender 3v2 3D printer and the Trotec Speedy 100 laser cutter. These 2 pieces of equipment are readily available in the UMPC laboratory with an operation difficulty suitable for students. At the same time, they can truly replicate the core processes of industrial rapid prototyping, achieving a perfect balance between performance and usability. The third question is, how to ensure the dimensional accuracy of 3D printed components? we adopted two key measures. First, optimizing FDM printing parameters, such as a 0.2 mm layer height and 50 mm S-print speed, to reduce extrusion variability. Second, calibrating the digital caliper with standard gauge blocks and performing multiple measurements for each key dimension to minimize measurement errors. The fourth question is, what challenges were encountered during manufacturing and how were they addressed? There were three main challenges: 3D printing warpage, which was mitigated by using a 60 degrees Celsius heated bed and hairspray to enhance adhesion, reducing the failure rate to below 5%. Laser cutting residues, which were cleaned using compressed air and isopropyl alcohol to ensure clean component edges. And measurement variability, which was eliminated through calibration and multiple measurements to ensure data reliability. These solutions are low cost and easy to implement, providing valuable references for other student projects. The fifth question is, can the prototyping methodology from this project be applied to other fields? The answer is yes. The core of the workflow we established lies in process adaptive design, cost control, and quality verification, all of which are universal engineering principles. They can be directly applied to custom automotive fixtures, anatomical educational models, and low-cost tooling development, among other applications. In summary, this project made us deeply realize that the core value of advanced manufacturing lies in the application of concepts and methods rather than relying on high-end equipment. Through this practice, we not only proficiently mastered key technologies such as 3D printing and laser cutting, but also enhanced our problem-solving and project management capabilities. We believe this project can provide a practical model for engineering education, helping more students deeply understand and apply advanced manufacturing technologies under resource-constrained conditions. We would like to express our sincere gratitude to IRT's Dr. Maaz Ayub Binti Hassan for her full guidance throughout the project, to the faculty for providing equipment and material support, and to all team members for their collaborative efforts. That concludes my presentation. Please take a look at this miniature anatomical model. As we observe its movement, it becomes clear that the natural range of motion in a normal human leg is actually quite limited. However, when we consider cases of severe leg injury or amputation, these structural constraints become the starting point for our innovation. Our project's design inspiration is drawn directly from the mechanics of this toy. To realize this, we used 3D printing technology to create a precisely scaled-down prototype. The key breakthrough lies here at the fracture point, where we have installed a specialized nesting structure. This unique mechanism allows the prosthetic to link seamlessly with the main body. Not only does this connection provide a much higher degree of flexibility, but it is also designed with modularity in mind, making the entire assembly incredibly easy to disassemble and maintain for long-term use.